Good afternoon. Section 7.2, trigonometric integration. So to motivate, we start with a simple example. Sine cubed x dx. Find the antiderivative or the indefinite integral of this. So we are going to use a trick. Okay, I'm going to split off. So you have 3 powers of sine here. I'm going to split off one of them and say that this is sine squared x times sine x dx. Okay. So now you notice that this is kind of a derivative of a cosine. Right? So with this idea in mind, I want to express everything in terms of cosines. And that's very easy because of the following identity. Sine squared x plus cos squared x equals 1. Do you remember this? So sine squared is easily expressible in terms of cosine. Okay? And here I have sine x dx. So now substitution is obvious. I'm going to say that u is equal to cosine x, and du is minus sine x dx, in which case this integral can be expressed as minus 1 minus u squared du. Okay. And what did I use here? I used the fact that dx of sine x is cos x, or rather I use this one, ddx cosine x is sine x. So one of these I used to evaluate this integral. And now we're almost done.
Professor, I think that's negative sine x.
Oh, thank you. Thank you very much. So this is important because we have a minus sign because of this. So I have u plus u cubed over 3. Or I can, I have to rewrite it back in the original variables, cos x plus cos cubed x over 3 plus c. Okay, so these kind of rules allowed me to evaluate this integral. And what else was important for this? You see, one of the steps, the first initial step was to split off 1 power of sine. Okay, so it's here. And the rest, sine square x, was expressible in terms of cosine by using this identity. So it was kind of lucky that this term was sine squared. If it was sine cubed, I would not be able to do this because I wouldn't know how to express sine cubed from this identity. Sine to the 4th, though, would be okay because it would be just this squared. So let me write down the 4th condition that I used here. We noticed that we had an odd power of sine. Okay? So this is what helped me. I'll show you in the next example to make this clear. So let's look at cos 5x sine squared x dx. Let's look at that one. So now I'm going to split off the power of cosine. So I have sine squared x. 1 power of cosine goes to the differential, so I have cos 4th x times cos x dx. Now, why is this a better expression than this? Because I can use these rules. So first of all, I notice that this is dx of sine x right? And sine squared x is already in terms of x. Cosine fourth I can express in terms of sine x in the following way. So cosine squared x is 1 minus sine squared x. Cosine fourth x is this thing squared. So I use a substitution. U equals sine x. Okay. Du is cosine x dx. And I rewrite this expression as follows. U squared, then I have 1 minus u squared squared du. You see, so it was good that this power was fourth. I was able to use this identity and simply square it to get cosine in terms of sine, or in terms of u. Okay, so here I had an odd power of cosine, and I used it. Let me finish this so you have the complete picture. So you have u squared. Now we have to expand the squares. The rest is quite standard. So I'm not forgetting to rewrite this in terms of sine again. Okay, so this is the answer. So with these two examples, either sine or cosine occurred with an odd power, and I used these rules. Okay. Now what happens if the power is even? So if both are even, so let's look at an example where we have cos squared x dx. So the power of sine here is 0, which is considered even, and the power of cosine is 2. These rules won't work, and then I have to use different rules. So here I write down two identities for you to remember, okay? So sine squared x and cos squared x can be expressed in terms of the double angle. Okay. These are called half angle identities, which I want you to know. Okay, so we use the second one of them to evaluate this integral. What I don't like about this integral is the second power. If I use the identity, I get the first power. So I get 1 plus cos 2x dx. What do I do next? The next is easy, right? The antiderivative of this is x over 2 plus sine 2x over 2 plus c. Over 4, actually. Another one, let's look at a more complex one. Cos fourth x dx. What do I do now? I use the same identity. I say that cos squared is 1/2 1 plus cos 2x. I square the whole thing to get the fourth power, and I'm good. Question?
Yeah, we substituted cosine squared with the half angle formula, didn't we?
Cosine squared. Oh, so this should be sine. You're right. Thank you. Very good. Thank you. So the fourth power is the same thing squared. What if I had the sixth power? Then I would take the same formula and raise it to the third power. Okay? So I can do any power if it's even by using one of these formulas. So in this case, I have 1/4 and integral of 1 plus 2 sine 2x plus sine squared 2x. And then I look at it, I say, oh, I have another square here, right? So what needs to be done? I go back and I have angle identity for the other one, for this one. So let's continue writing. I have 1 plus 2 sine 2x. So sine squared is 1/2 1 minus cos of what? 4, right? Sine squared of 2x, 2x becomes 4x. Okay? Dx. And at this stage, I can simply take the integral. So I have x plus minus cos 2x plus x over 2 minus sine 4x over 4 plus c over 8. So lots of factors of 2. Questions? Question?
Why is it sine 4x again?
So this is an antiderivative of cosine 4x. So why is this cosine 4x? Because of this, right? This sine squared x is 1/2 1 minus cos 2x. Sine squared alpha x is 1/2 1 minus cos 2 alpha x. So if this is 2x, this becomes 4x. If this is 3x, this is 6x. Okay, that's why I got 4x over here. Question?
Can you show how you get sine 4x over 8, like step by step?
So I have to take what is the antiderivative of cos 4x? That is sine 4x over 4. The number 8 comes from this factor 2. So let me summarize everything that we found. So basically, we have looked at integrals that involve powers of sine and cosine and nothing else. So we look at integrals of, I don't know, sine, k, x, cos, j, x, dx. Things like this, okay? Depending on the powers, we have different techniques. So number 1, yes, if power of cosine is odd, we save 1 power of cosine and use the substitution u equals sine x. If the power of sine is odd, we save or split 1 power of sine and use u equals cosine x. Here in brackets, what if both of them are odd? Then I don't care, I can use either, okay? If both powers are odd, it's the easiest case. I can either use this substitution or that substitution. The harder case is when neither of those holds. In this case, we have both powers are even. And then we use double angle identities or half angle identities. Use half identities. As you have seen, sometimes you have to use them more than once. Okay? Questions? So all these cases are mapped out here. There's nothing else, no surprises. It's a clear algorithm which tells you what to do. The next topic is when we go to tangents and secants, and then it's a little bit more interesting. So to draw an analogy, actually, let me use this part of the blackboard. We're going to look at things like tangent kx secant jx dx. And it's kind of analogous because we have an identity. So here we have sine squared x plus cos squared x. What's the analogy here? We have secant squared x equals 1 plus tangent squared x. So it's very similar. And we know how to differentiate tangent. What's that? That's secant squared x. And when we differentiate secant, we get secant tangent, right? You know these rules. So the analogy is that they're completely kind of interchangeable. The derivative of one is expressed in terms of the other, more or less. So and they satisfy this nice identity which involves squares of the two things. So hopefully we'll be able to integrate such objects. And we start from some simple examples. So the first one, let's look at tangent squared x secant fourth x dx. So you have to know the tricks, okay? I'm going to do the following. I'm going to save 2 powers of secant. So I have tangent squared x secant squared x times secant squared x dx. So I saved 2, and that's going to be the derivative of a tangent. So I say u equals tangent x. So du is just that, secant squared x dx. Okay, so this guy is du. Now this is u squared because it's tangent. How about secant squared? For that, I go to the identity, and I realize that secant squared is 1 plus u squared. So this whole thing becomes u squared 1 plus u squared du. And do you allow me to put dot, dot, dot here? Because this is easy, right? Okay. So what was the trick? I saved 2 powers of secant to make the derivative of a tangent. Now, let's look at the next example. Tangent cubed x secant fifth x dx. Okay. So here, I'm going to save 1 of each. Okay. I'm going to save 1 tangent, so I have tangent squared x, and 1 secant fourth x. So I have tangent x secant x dx. What is this? What I saved, I'm arranging for myself to have a derivative of a secant. So u is secant x, therefore this is du. This is u to the fourth because it's just secant, and tangent is secant squared minus 1. So this is u squared minus 1. So the whole thing becomes u squared minus 1 u to the 4th du dot dot dot. And there is a certain pattern to this, right? So what I want to achieve is the following. You see, in the first example, my new variable is a tangent. So whatever under my integral is already expressed in terms of tangent, I don't care what it is. It could be tangent to the first power, second, third, any function that I don't care. Secant is a problem because this is the one I will have to express in terms of tangent through the squares. So the remaining power of secant has to be even. And so I saved two of those, so I should have started with an even power. So this has to be even, and this is even. So this gives me my first case under this heading. If secant is even, okay, then we save what? Secant squared x, and we make the substitution u equals tangent x. Okay. If the power of secant is even, when I save two of those, the remaining power of secant is even, and I can use this. This is the point here. In the second example, I saved one power of tangent, one power of secant. So my variable was secant. So I want the tangent to be even. So the remaining tangent is even. So I have to start with tangent is odd. And there is some, at least one secant. So in this case, we save tangent x secant x and use u equals secant x. Okay. So these are two cases, but unfortunately they do not exhaust all logical possibilities. So what is left here? I'm going to say the following. So let's suppose that secant, let's suppose that neither of these holds, okay? Secant is odd, and tangent is even. Then I don't know yet. All right, we put a question mark. And there's a fourth possibility. Tangent is odd, and there is no secant. So if tangent is odd and there's no secant, I cannot save one power of secant to arrange for this. Okay, so that's another thing that we'll have to explore, and these are difficult. So let me start maybe we can number them. So this is A, B, C, and D. I'm going to start with case C. So secant is odd, tangent is even. Let's design the simplest example of a power where secant is odd. So say secant x, first power. Tangent is even. The smallest even power is 0, so no tangent, dx. Okay. So this is my first example. And you won't believe how difficult this is to take. It requires a substitution, which I believe is very difficult to guess unless you know the trick. So let me show you. It's very strange. So I'm going to rewrite it like this. Secant x, okay, and I'm going to multiply and divide this by the same thing. So this is secant x plus tangent x divided by secant x plus tangent x dx. So nobody can say that this is wrong, right? I divide and multiply by the same thing, but why, right? It seems completely arbitrary. So then I use a substitution. Let's set u to be that. Secant x plus tangent x, and just try it. Okay, so the next step is always to calculate du. Secant x tangent x plus secant x squared. Okay. So I'm going to continue writing here by multiplying through the numerator by the secant. So I have secant squared x plus tangent x secant x plus tangent x dx. So I haven't done anything but multiplied through. And now you notice that the expression in the numerator actually coincides, dx here, coincides with this derivative. Right? It's like magic. So what I have on top is just du. What do I have in the denominator? U. Look at this. Okay, so it works. And it takes some clever person to guess, right? It's completely not trivial. So what's the antiderivative? That's a log of the absolute value of this. So we have a log of that whole thing. Secant x plus tangent x plus c. Okay. So the antiderivative of secant is evaluated like this, and is expressible in elementary functions in this way. Okay. It's a good idea to memorize it. To memorize these steps and to memorize the answer maybe. Okay. So that was the simplest non-trivial example of part C. Secant is odd, tangent is even. I'm going to next consider the next simplest case, which is secant cubed x dx. Right? So again, like with many of these in part C, unfortunately, there is no algorithm or rule that you can just apply. Okay, it's kind of like an art here, and each case happens to be different. So this one, if you have done enough of them, perhaps you can discern some patterns. So let's practice. So with this one, I'm going to split off secant squared like this. And now we're going to use integration by parts. Okay, so I'm going to set two functions. U is secant x, and v prime is secant squared x. Okay, so it's easy to find u squared. U squared is secant tangent x, and v is the antiderivative of secant squared. So this is tangent. So let's try to take this guy by parts by using the usual formula. Secant x tangent x minus secant x tangent squared x dx. Okay, not clear what we gained, but let's continue. And we notice that here we have tangent squared, and we're going to express it in terms of a secant. Okay. Secant x tangent x minus secant x secant squared x minus 1 dx. And I'm going to open the brackets here. Secant x tangent x minus secant cubed x plus secant x dx. So a lot of calculations, and what is the result? On the left, you find the integral of secant cubed. And on the right, you find blah, 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 secant cubed x, the same thing. Okay, so actually we arrived at an equation which involves the unknown integral as a variable. I bet you saw that the day before yesterday. I wasn't here, but one of the integrals that you take by parts involves this technique. So I'm going to call this I. So what do I know about I now? I know that I is equal to secant x tangent x minus I plus secant x dx. And this is not a bad equation. You can solve it, definitely. It's an easy equation. We can say that I bring it over to this side, right, is equal to 1/2 secant x tangent x plus secant x dx. Finally, I'm going to use my first example. Question?
You're lost.
Which, is this clear?
Where do you get tangent squared?
This one?
Yeah.
Oh, so this is over here. Let's elaborate on this step. So it's equal to uv minus an integral of u prime v, right? This is the usual formula. So this is uv. And so what is u prime v? I have to take this line. U prime is secant tangent, and we have v, which is tangent. I just multiply them together. So I have secant tangent tangent.
I got you.
Question?
I was going to ask, could you also split the secant cubed into 1 plus tangent squared fragments? Because that would also be equal to secant plus tangent squared secant, wouldn't it?
Fragments. So you're saying that this is 1 plus tangent squared
Times secant.
times secant.
Which then would multiply out to secant plus secant tangent squared.
Okay, and then what?
Well, then you can integrate them both separately. You have to deal with an integral of secant by itself anyway. That's really the ugliest one. And
So
then-
the secant is easy, yes. How about this one?
Well, that one you can do the u substitution, or...
No, you can't.
Well, there was also...
It doesn't fall into any of these categories. So tangent is not odd, and secant is not even. So see, this is tough because by doing this you cannot. A nice thing would be to reduce it to one of these, and this proposition doesn't lead to any. So perhaps there is another way of doing it, and perhaps it starts here, but I don't know where to go from here. Okay. Good question. So let's write down the answer here. So it's 1/2, and we have secant x tangent x plus this logarithm of secant x plus tangent x plus c. Okay. So this is how you can evaluate such an integral. Questions?
Why is it plus? Oh, wait, don't answer.
Okay. So the trick here was to see integration by parts, okay, where it wasn't really obvious, and then find an equation for I. So basically we reduce it to the same thing. Okay, so now And you realize that these are two case studies of case C, and there is no general rule. Okay, so I think there may be another example in the textbook, but there is no general rule. Now let's look at case D. Tangent is odd, and there is no secant. So basically, odd powers of tangent. And the first one is really easy. I don't know what to write. Okay, I'll write here. So, case D, basically any odd power of tangent. What's the simplest integral of type D? Tangent x dx. Okay, and that is easy. What we do is we say that tangent is sine x over cos x dx. And what's the next step? Substitution. You say that u is cos x and du is minus sine x dx. So this is du over u. Like this. So it's a hidden substitution. Sine x over cos x, and the sine is a derivative of cosine. So we end up with a log. Questions? Okay. The next case, we are looking for odd tangents, no secant. So the next one obviously is tangent cubed x dx. So what do we do here? We are going to split off tangent squared. Okay, tangent squared x dx. And for this one, we're going to use the identity where we express it in terms of secant. And now we open the brackets. Tangent x secant squared x dx minus tangent x dx. So tangent x secant squared actually does happen to be one of the simple cases. Is this one. You can see that secant is even. Okay, so this one we can do easily. And this one we just did. This is the first power of tangent. So for this integral, we can use a substitution. U equals tangent x. Okay, and du is secant squared x dx. So let's continue. We have u du simply minus, and for this one we use the result that we obtained, log of cos x. Okay, so we have u squared over 2 and finally we rewrite it in terms of tangent. And that's the answer. So normally with these ones, you can reduce them to a previously solved one, just like this. Okay. Okay. So now the last little topic for today is a slightly different type of trigonometric integrals. It has a different form. So instead of powers of sines and cosines, we're going to look at the following combination. Sine mx cos nx dx. So these are not powers. These are arguments of the sine and cosine are given by mx and nx, where m and n are some numbers, some constants. So this is not the only type. We could have, for instance, sine mx sine nx. Or we could have cos mx cos nx. Okay? There are three different types. Sine, cosine, sine, sine, and cos, cos. And these are easy, okay, because here we have a fast rule. We have a rule that if we follow it, we are guaranteed to have a successful integration. The rule involves identities of the following type. So let me write them down. On the left, I'm going to have a product of sine and cosine of different arguments. Okay? So product on the left. On the right, I'm going to have a summation, which is a lot easier to integrate. So I have 1/2 sine of a minus b plus sine a plus b. Like this. So I'm going to have 3 of those. The next one involves sine A, sine B. Okay. Similarly, I end up with a sum, cos A minus B minus cos A plus B. And the third one is cos A cos B. So the ones on the left are hard to integrate. The ones on the right are easy to integrate. That's what we're using them. Let's consider a specific example. Sine 6x sine 11x dx. Okay. So which formula are we going to use? Sine, sine. It's the second formula here. So I'm going to rewrite the expression under the integral as 1/2 of cosine of 6x minus 11x minus cos of 6x plus 11x dx. Simplify. So here I have a cos of minus 5x minus cos of 17x dx. And remember that cosine is an even function, so cosine of minus 5x is the same as cos 5x, right? And now it's very easy. I have to take the antiderivative of these things. There's one little hidden step here, which is a substitution. I can say u is equal to 5x. Okay, that gives me sine 5x over 5 minus sine of 17x over 17 plus c. So these are always done in a standard way. Questions? Very good, thank you.